Okay, I think it's a good time to start. I hope everyone can hear me well. Welcome again to our department seminars of Hacettepe University Electrical and Electronics Engineering. I am Ismail Yanık. I am a faculty member in the department. Also, my partner today is Barış Yüksekkaya hocam, Dr. Barış Yüksekkaya. He will be taking a lot of responsibility for this event, and we will be hosting Dr. Emil Björnson from Linköping University. I will make some quick announcements, and then I will let the stage for Barış Hoca so that he can introduce our visitor today. During the meeting, I will be keeping everyone's microphones muted, but if you have any questions, if you raise hand or write to chat, we can let you activate your microphones. And possibly we will have a question session at the end of the presentation. The meeting is also live streamed on YouTube. So if you wish, you can also watch it on your devices. So on YouTube, you will see a live YouTube icon on the top left corner. I think that's all for my side. I thank again our visitor today, and then Barış Hocam, you can continue.
Thank you, Ismail Hocam, for the introduction. I'd like to say welcome to everybody to our department seminars. I know that most of you know Professor Björnson, but I want to give some information before his speech. Professor Björnson received his MS degree in engineering mathematics from Lund University in 2007 and the PhD degree in telecommunications from the KTH Royal Institute of Technology in 2011. From 2012 to 2014, he held a joint postdoctoral position at the Alcatel-Lucent Chair on Flexible Radio Supelec, France, and the KTH Royal Institute of Technology, Sweden. He joined Linköping University in 2014, where he is currently an associate professor. In September 2020, he became a part-time visiting full professor at the KTH Royal Institute of Technology. He has authored the textbooks Optimal Resource Allocation in Coordinated Multi-Cell Systems and Massive MIMO Networks, Spectral Energy and Hardware Efficiency. He is dedicated to reproducible research and has made a large amount of simulation code publicly available. He has performed MIMO research for over 10 years, and his papers have received more than 10,000 citations. Also, he has filed more than 20 patent applications. He has received the 2014 Outstanding Young Researcher Award from IEEE Communication Society. And he received the 2015 Ingvar Carlsson Award. He also received the 2016 Best PhD Award from EURESIP, the 2018 IEEE Marconi Prize Paper Award in Wireless Communications, the 2019 EURESIP Early Career Award, the 2019 IEEE Communication Society Fred Ellersig Prize, and the 2019 IEEE Signal Processing Magazine Best Column Award. I would like to thank Professor Björnson on behalf of our department again for accepting to attend to our seminars, and I leave the stage for him right now.
Thank you very much for the introduction. So this is a good honor, and it's sort of the great thing now when everyone is home, that when you are giving a seminar at the university somewhere in the world, well, now it's not only the people that are in that city that can attend, but now everyone online can attend. So thank you for either seeing this presentation live or actually watching it afterwards on YouTube if it's live streamed there. So I'm Emil Björnson. You already heard my credentials. I will talk today about pilot contamination, which is a nut that we will try to crack, and to sort of focus on what this is all about. What is pilot contamination? I will talk for an hour to provide you with the background, both to what pilot contamination is, where does it appear, and then how do we solve it. So we've already gone through my background, so I will just go straight to the outline of this talk. So first I will talk about massive MIMO, the new 5G wireless technology that this pilot contamination phenomenon is particularly appearing in, and I will provide the background on that. Then, when we have introduced what is pilot contamination, when does it appear, how does it appear, we will talk about ways of decontaminating, removing this type of problem, because this is sort of a nut that contains inside of it the key to providing any data rates that you would like in a wireless system. Any number of users could share the performance or so. But we will need to crack the nut in order to actually reach that. And is that possible or not? That is sort of what this presentation is going to be about. And towards the end, I will present a method that actually solved this problem. And that was sort of there all the time. We just didn't see it. And I've been working on this massive MIMO area for almost 10 years. And it took me many years before I observed that this thing appeared as well. So I will start by talking about the basics of massive MIMO and pilot contamination. So let's start at the simplest level. We are talking about cellular communications. So these are the mobile phone networks, for example, where we, in order to be able to deliver from the beginning coverage for phones, but later also data services, provide such coverage all over the cities and all over the world, we need to put up infrastructure, these base stations that are illustrated here. And each base station is then taking care of covering all of the users that are close to it. That creates the world division into cells like this. So cell network contains cells. Each cell contains a base station that is fixed at some location and the number of users that are turning on and off and being served by that base station. And when we are building new cellular networks, now, for example, 5G is being rolled out, it's sort of about making these cellular networks more efficient. And how can we do that? Well, one way of breaking it down is to talk about the throughput, the number of bits per second we can deliver, and just not to one user, but in the network as a whole. So we measure the network throughput in bits per second per square kilometer. And the square kilometer could here be a city, or it could be an entire country, for example. So if we would like to increase something like that, one way of breaking this problem down is to look at an area. This is a certain number of square kilometers, and we have a certain number of users here. Then a simple formula for this network throughput is that the throughput in bits per second per square kilometer can be divided into 3 different factors. The first one is the cell density. That's the number of cells per square kilometer, the number of base stations we put up in this region. The second thing is the available spectral available frequency spectrum that we're having measured in hertz. So it can be different frequency bands. The collection of them is what goes in here. And then we have the spectral efficiency, which is sort of something that is determining how efficient our technology is at every base station, measured in bits per second per hertz and per cell. So if you multiply these units together, you see you get bits per second per square kilometer, which is a good way of validating that this formula makes sense. And conventionally, when we have been improving our cellular networks, it has been a lot about trying to increase the cell density. So put up more base stations, and densifying the distance between them has become smaller and smaller. And this makes good sense, but nowadays, the distances are very small. So from the beginning, there might have been like 10 kilometers between base stations, and nowadays there might be 100 meters in some cases in the city centers. So it started to be more and more expensive to put up more base stations. The second option is also something that we have been utilizing every time there is a new generation of cellular networks. New spectrum bands are added to the system. And the spectrum resources are scarce. In particular in the band between 800 megahertz up to 3-4 gigahertz, where all of the systems of today are operating, it's very hard to find more spectrum there that is not already used for cellular or for some other wireless service. And then people can say, well, look, there is all this millimeter wave spectrum up at 28, 35 gigahertz, maybe 60, 70 gigahertz. Yes, there's a lot of spectrum there. And they have been used for a long time for fixed links, sort of from a satellite down to Earth or between 2 base stations that want to talk to each other. But they're very hard to utilize for users that are moving around because the channel conditions are very bad. So as long as it's only when you can guarantee to have a line of sight, you see the base station that they're going to work very well. But now in 5G, will eventually be utilized as well. The third factor is the spectral efficiency. And this is the thing that haven't been improved that much over the years. But it's sort of the new aspect, well, have been there all along, but it's a thing that we try to now put a lot of emphasis on. And this is what the massive MIMO that I've been working on is about, and where also 5G is excelling. So it's essentially about improving the technology that goes into each and every base station. And upgrading the base stations, you don't necessarily need more spectrum or put up more base stations, but you improve every base station. Then, of course, in reality, we will make use of all these three, but the focus in my talk will be about the spectral efficiency. And my focus will also be on systems that have fairly large coverage, where there can be many users served by the same base station. Think about the conventional base stations that your mobile phone are talking about, operating a spectrum below 5 gigahertz. And why is that? Well, that is where all the systems are working now. And when we're putting up 5G base stations, that is also still where all the systems are operating. So the 3 gigahertz band is where most of the 5G base stations are operating. So how do we increase the spectral efficiency? Well, if we start with a simple scenario, we have one antenna here that is communicating with another antenna. Then you might have seen the channel capacity formula, which is essentially saying that the number of bits per second per hertz and per user or per transmission like this that we can transmit is governed by the log of base 2, or 1 plus this ratio here, which is a signal to interference and noise ratio, or in some cases it's only signal and noise. So it's the received signal power divided by the interference power if there are other interference transmission at the same time, and the noise power. We add those two together, we compute the ratio, we put into this log 2 or 1 expression, and that gives us the spectral efficiency of the transmission. And if this ratio is fairly small, logarithm behaves like a linear function, so things are fine. But as soon as we are reaching a fairly good spectral efficiency of, say, 4 bits per second per hertz, that is what your mobile phone will utilize under good conditions, then it becomes very hard to improve it. If we would like to double it from 4 to 8, well, then we need to increase the signal power a lot, because this logarithm here is forcing us to increase it to a large extent. So we need actually 17 times more signal power in order to increase this from 4 to 8 bits per second in hertz. So that's what this graph here is also showing. We increase the power linearly, but once we are reaching the logarithmic path of this function, then it grows very, very slowly with power. So this is not the way to increase the spectral efficiency. What is instead, the key word here is that it says per user. So we could serve multiple users at the same time. So the key is to have many parallel transmissions. So conventionally, if we have a base station with just one antenna that sends out the signal in all directions, or at least focus within a particular sector direction, like 120 degrees, and all the power is equally spread inside there, well then, if you have 2 users, they will see the same signal, and there's no way to separate between them in a good way. However, if we are using an array of antennas that are transmitting 2 signals with different delays, you can make sure to create a directed transmission to user 1 and another directed transmission towards user 2. So this is sort of utilizing this constructive and destructive interference things that you might have seen in physics classes. If you have multiple sources or waves, they will at some locations add up constructively. In some places, they will cancel out each other. And that is what we're using here. We send out the same signals with different delays so that we are creating constructive interference at the user of interest. And then at the same time, we can send out another signal with constructive interference at the other user of interest. So if we have 2 transmissions at the same time, we have 2 users. So we can take this formula and we can just multiply by 2 in front of it. And that is what multiple antenna communications is about. And this field have a long history. So you can trace back actually base station with multiple antennas goes back 100 years when people were trying to communicate over the Atlantic. But when it comes to actually sending multiple streams, this is a concept that appeared in the late 80s and early 90s. And at that time, it was more like an engineering solution. And so here's a paper from 1990, where they were showing, okay, we have base stations, now we have cars that are driving around them, we send different beams towards them. And that is sort of revealing why people were talking about car phones in the past. Okay, and then the problem was that this was not very successful at the time. One reason was probably that the information theory around how to operate a system like this wasn't there. It wasn't until the early 2000s, I think 2004 was a golden year, when a lot of papers that were saying how we should operate this in a good way actually appeared. So here, the concepts and also patterns were appearing much earlier than the actual theory. Then later, in the 1996, around so the late 1990s, there were concepts and patterns around what was called at that time layered space-time architecture, or single user MIMO. And I should say that this concept here with serving multiple users from the same base station with different direct transmission was called at that time space division multiple access. Nowadays it's called multi-user MIMO, where MIMO stands for multiple input and multiple output. So it's the multiple antennas at the base station and the multiple users or cars that are served at the same time. So here we serve multiple users, but in the late 1990s, we started to actually use computers and phones for data services. And then the data rate became important. It wasn't as here that you wanted to put up a base station and serve as many cars as possible that all could make phone calls. Well, here you actually like to push up the data rate. And that's why the idea came that, well, instead of serving multiple users, can't we on this house here put up multiple antennas? And if there are different paths here, one signal path via this mountain, one direct one via this reflecting houses, then you will be able to send multiple data streams to the same house. So it's sort of having multiple users, but they're all on roughly the same location. And this was something that actually was implemented earlier, even if the concepts and patterns appeared later, because the theory for doing this was there. Then in the 2010, around that, the idea of massive multi-user MIMO, or just massive MIMO, appeared. It actually was called large-scale antenna system at the time. So there's a lot of different names for different things. But this was sort of to go back to the basics, this concept of serving multiple users, but making use of the information theory that appeared later and redo it in sort of the right way, the way that was working the most. And what was observed was that we want to serve multiple users, but not by having, say, 3 users and 3 antennas here, but to have maybe 3 users and 30 antennas. The more antennas you have, the more directive your constructive interference in certain directions is going to be. And that can be utilized to send narrow beams, as was illustrated here, towards different users with strong focus of energy and little interference in other directions. So strong directivity, small side lobes, that is sort of when you direct in one direction, how much energy that are leaking at in other directions. So in that way, we could put a lot of energy where we want it to be, and we could be sure that there will be little interference at other locations. And this was a concept that Thomas Mercetta was pointing out in particular. And what has then happened since 2010 is a lot of things. So I would say that when Thomas Mercetta was presenting his first works around massive MIMO, where he didn't just have like 30 antennas I was mentioning, he was writing a bold paper about having an almost infinite number of antennas and looking at things that were happening in those cases. And we will come back to exactly how to do that. But people were rather skeptical and viewed as that here is this guy who every time he shows up, we have 10 times more antennas as the last time this was here. And this doesn't make any sense. It was some kind of science fiction idea. But it has become mainstream in just 10 years. So in the 90s, those people that were inventing the multi-user MIMO technology, they were putting up some base stations like this circular array here in Tokyo, for example. They're still there. I saw them when I was there a year ago. And it wasn't very competitive. They tried it out at that market. It didn't perform well enough for other markets to pick it up. And I think some of the reasons was that it was easier to just put up more antennas, more base stations than putting up more advanced, expensive base stations. And the system were too small. They had like 8 antennas to try to serve 8 users. And even if you can direct the signal, there were too much interference that leaked. There were no information theory behind them, as I was mentioning. So they just tried to design them as an engineering effort. Probably did the best, but they didn't get the best result out of it. And also at that time in the 90s, people were primarily using their phones to make phone calls and not to transmit data. So the important thing was not to be able to serve as much use as possible when it comes to multiplexing and pushing up the data rates. As long as the user was covered, that was fine. Doesn't matter if you could direct the signals and get 100 times stronger signal, because if you hear the person, you hear the person. And when I started to go into this massive MIMO area, I active in the 90s and said that, well, if you're going to build something like this, it's just going to be too large, too expensive. Just look at these boxes here, they are large. And this is for 8 antennas. Say that you would have, maybe there are 10 in that picture or so, but if you're going to have 100 antennas, you're going to have 100 boxes and 100 cables to each of them. It makes no sense. And the complexity is going to be too high. And there are no actual practical gains because there is not enough users in most places to utilize something like this. You need to serve 10 users, but most people are downloading a small piece of data and then they do something else. But they were actually wrong. And now when 5G has appeared, massive MIMO is everywhere. So here's a graph showing from the Global Data Institute how many actual massive MIMO products that the different companies, Ericsson, Huawei, Nokia, Samsung, and CTE have. So these are with different sizes, 16, 32, 64 antennas, or some other variants when they are combining multiple antennas with antennas in other band and things like that. And you can see that some companies have like 15, 20 different products of the different sizes. These are typically for different markets, different form factors, different frequency bands, and things like that. But there is a lot of these base stations there. And I heard that Huawei, they have sold 1 million base station of this kind, 32 and 64. So half of them are being deployed in China now. So there is massive MIMO base stations in all of the countries where 5G is being used now. So if now people were skeptical from the experience from the 90s until today, how to build something like this, what is it happened that made it possible to build something like this? Well, I think the hardware evolution have sort of catched up with what people have in their mind when they developed the first patents. So back in the days, step one, when it came to putting up base stations, was that you put a passive antenna, an antenna with a fixed directivity covering a sector, up on the rooftop or up in the mast somewhere. And then from that antenna, there were a long cable down to a radio unit that is creating the radio signal that is going to be transmitted. And that signal was then going up to the tower. There were a lot of losses there between them, but the radio unit was too large and heavy to put in the mast. So that's why we had to have that distance. And then next to it, there was a so-called baseband unit that was sort of creating the signal that was going to transmit. So digital signals, and here you had an analog signal, and then you send that over a long cable up to the antenna that re-radiates it. In the beginning of 4G, this started to change because the hardware had been improved to such an extent that you can create a small radio, small enough so you can put it up in the mast next to the antenna. So this cable here became very short. And then you could have a digital cable. Digital cables, you can have fiber cables that are very long and they're not losing any energy along the way. It's this purple cable that you would like to be short. And that was happening in 4G. And then towards the end of 4G era, now in 5G, what has happened in addition is that the radios have become even smaller, that we can put them into the same box as these antennas here. And that is when we can build an array with, here you say 8 by 8, so 64 antennas. They are small passive antennas. Behind them, there is a radio unit that is generating the signal. And then you can integrate this all into one device. And that is where you actually have the possibility of putting a lot of antennas, a lot of radios into the same small box without having hundreds of cables. And then you still need a fiber cable down to some kind of baseband unit that is designed in signals. But the new thing is also that you can put it elsewhere. You can put it in the cloud somewhere, not kilometers away, but maybe a few hundred meters away, and maybe the same hardware here can be utilized for multiple base stations, things like that. So this is sort of the edge computing that people are talking a lot about today as well. So hardware have catched up. And here is sort of an example of what is going on now, what has been happening over the last 10 years. So before, sort of the major deployment was this classical antenna arrays. One signal in from one radio. You might have multiple elements here that are together forming a very directive signal down towards the Earth and into a particular sector. But it's always the same directivity. And now we have been moving towards these so-called massive MIMO arrays with a lot of inputs to it. Each of these elements here, there are 64 of them in this one. Each of the elements is a small antenna that is radiating in a fixed way, but they're connected to different radios that are put behind it. And in that way, we can create signals. We can send to every radio, we can send the same signal but with different time delays to create a yellow beam. You can do the same thing to create a purple beam, and the green beams and all these beams can be created. And then we add up the signals, and then we can, at the same time and same frequency, we can send signal to multiple users in different directions. 64 low gain antennas that are creating directive transmissions in different directions, serving different users. And in some cases, you can sell 2 beams to the same device here if the device have multiple antennas for different polarizations. So we use this many antennas to serve many users and to spatially separate them. It's just like having one binocular looking in one direction, one binocular looking in another direction, but you do it at the same time. Yes, and I can say, by the way, here as well, that this is the type of equipment that are put up everywhere now when we have massive MIMO, or when we have 5G deployment at all, in the US, in China, in Japan, or Korea, Sweden, probably in Turkey as well. When 5G is being deployed, it's particularly in what is called the mid-band, 3 gigahertz bands, where there's new spectrum, where these arrays are put up at places where there's a lot of users, so we can make use of this feature. So here is an example of what this product could look like. And here have been focusing on the 2 to 3 gigahertz band, just because I could find specs particular for that. So this conventional antennas that I was showing on the left, and I can't see the entire number here, but it's roughly a meter tall, and 15 centimeters times 7 centimeters. That is the tall antenna, fixed directivity. And then the new 64 antenna, Ericsson hardware, and the other companies have similar hardware. It's also a meter tall. It's not really as tall as this one. It's wider instead. So we put multiple antennas horizontally and vertically. We separate them up into 2 dimensions. We can send different directions horizontally and vertically. And the reason that I show you this is that when we say that something is massive here, we are talking about that this one have 1 radio, this one have a massive number of radios. It's not massive in size. It's not that much larger. And that's why when you put this up on the rooftops, it won't look much different. There's a lot more hardware into it. So this one is weighing 60 kilos as compared to this one that is substantially less heavy, but still, it's there. There is 1 million of them out in the world now. So let's now go into a bit more technical discussions. What is massive MIMO? Well, for a long time, massive MIMO was this word that was floating around. Thomas Mercetta was sort of coming up with the idea of having a lot of antennas, serving a lot of users. He had written a book around that topics as well. And in his book, or in the first paper, there was no clear definition of it. So it was first when we were writing our book, Massive MIMO Networks, where we dared to provide a more strict definition. So it's a cellular network where the base station have many antennas, M, and I would say that you need at least 64 antennas to call this massive MIMO. Then you are spatially multiplexing many users. So you should support to serve at least 8 users. And this is satisfied by at least some of these massive MIMO base stations that are being deployed now. And the key thing here is that you have a ratio between the number of antennas, M, and the number of users, K, which is much larger than 1. So in this case, the ratio is 8, for example. Then, of course, the number of users are going to change over time. Sometimes you have 1 user at night or 0 users, and sometimes you have maybe the maximum number that you can support, 8 or 16 or something like that. But in the intended use cases, you have many more antennas and users. So you can send a beam towards the user, very directive. And when you do that, the risk that there's another user nearby is small. So you sort of, with having many more antennas and users, you're creating some room in between the users when you are directing the signals. And importantly, this is a non-orthogonal scheme. You might have heard the term non-orthogonal multiple access, or NOMA, which is sort of a way of using a single antenna transmitter to serve multiple users. That is like old school 90s technology, even if it has sort of come back for whatever reasons that I don't really understand. But this is sort of the non-orthogonal multiple access 2.0 or 3.0, where you have multiple users, you serve them at the same time and frequency. Non-orthogonal means that when I'm directing a signal at you, your neighbor that I can also serve at the same time, you won't be orthogonal. There will be interference between you. And that is what makes it challenging to handle. But if there is a struggle there is also a gain if we are able to serve both of you and control interference. Well, then we are doubling the transmission rates and the spectral efficiency. So the way that this is going to work, when you operate the system like this, we have the problem that the channels, the communication channels, the ways that the signal propagating from the base station to the users and back is changing, because you are moving around or objects are moving around, that those objects were reflecting the signals towards you. So that is changing the channels in time. And also when you have different objects, different distances, if you are considering a transmission that happens at one frequency or another frequency, which is say 300 kilohertz away from it, it will react differently, because the physical distance are the same, but the delays that you're seeing of your signals when they have different frequencies varies. And that is also changing variations over frequency for these different channels. So the way that we are normally operating a system like this, when we know that the channel is going to change over frequency and over time, is that we divide the frequencies and the time into frames. And we design these frames so that within such a frame, the channel is going to be fixed, both over time and over frequency. And when we select the size of it, we are keeping in mind 2 things: the coherence time and the coherence bandwidth. The coherence time is how much time it takes for a user to move before the channel is changing. And most users are not moving, so you're sort of designing for the worst case. If you are going to serve a person that is running, there's one speed, people that are walking, one speed, and people that are driving on the highway is another speed. So the faster you are moving, the smaller is the coherence time. Coherence bandwidth is sort of telling how long are the delays from the shortest to longest path that signal can take from transmitter and receiver. And the longer those delays are, the smaller is the coherence bandwidth. And yeah, you need to build your system for one coherence time, one coherence bandwidth, and you live with that. And then you sort of try to conform everyone to that, or you select the kind of worst case conditions. And within the frame here, you can transmit a certain number of times. And we know that from the sampling theorem that if you are sampling a signal that have a bandwidth of BC, which is the coherence bandwidth, then to represent it, you need 2 BC samples per second. And those are real valued samples. And if you view them as complex valued samples, we need only BC, such samples per second. And then how much time did we have in the frame? We had TC. So if you multiply these things together, BC times TC, that's what's written here. That is number of symbols or samples, whatever we want to call them, the number of unique transmission occasions that is fitting into a frame like this. So that is sort of our opportunity to send signals that many times, and then the channel is changing. And that means that we sort of need to do three things. We need to learn the channels, and that is done in massive MIMO by sending a signal from each of the users to the base station. And that signal allows the base station to learn the channel. It's a known signal. So it's sort of the known signal propagates over an unknown channel. And then we can learn the unknown channel. And then when we know the unknown channel, an unknown signal can now propagate over the known channel. And then we can learn that signal, which will contain the data. And the rest of the frame is used for uplink data and downlink data. We can divide them between uplink and downlink in the way we like. So uplink is from the user to the base station, and downlink is from the base station down to the users. And in cellular networks, other conventional kinds, we typically have like 200 of these symbols. But if we are building it only for indoor uses where people will at most be jogging a little bit and the reflections will not be hundreds of meters, but only tens of meters, well, then we can get up to 10,000 or even 100,000 transmissions within a frame like this. Okay, so the notation that we should remember, tau c, that is the number of symbols, number of times we can transmit in the frame before the channel is changing. And tau p, that is the number of symbols we are assigning to send pilots from users, known signals that allows us to estimate the channels. And the remaining thing, tau c minus tau p, that is what we're using to transmit data. And that is where we are measuring the spectral efficiency, how efficient our transmission is. We are going to look at both of these things, how efficient our transmission is and what we can do with the pilots. And before we go into that in detail, I will make use very soon of something called the law of large numbers. And there's different versions of that. There is a weak, there is a strong, there are different variants of both of them as well. The version that I will use, I call it Lemma B12 here, that is referring to my book, Massive MIMO Networks, but this is the standard result. What the law of large numbers says is that we have a sequence of random scalars, x1 to xm. In this case, they are non-negative. They are independent and identically distributed. They have a certain mean value. So if you take the mean of any of them, it's equal to a. And you see this a here is not depending on the index m, because it's the same for all of these random scalars. And then there is some assumption that if you take the signal and we take it to the power of 4, then this expected value is smaller than infinity. So it says something that around this mean value here, there is some variations, but they can't be infinitely large. Then if we are taking our m different realizations, we add them up, we divide with the number of them, and in that way we'll compute some kind of sample average, then this sample average will converge towards the mean value when you have very many terms, as the number of terms is going towards infinity. And this happens almost surely in the strong law of large numbers, and there are other cases, weak ones, where you can have other types of random convergences, and that is not the important thing, what type of convergence we're actually having. We will use this one very soon. We will use it for a case like this. We have a vector, x, so boldface here is representing a vector. It contains x1 to xm. These are ID random variables with some bounded second order moments. So each of them have a variance that is bounded. Then if we compute the squared norm of this vector and divide with the number of elements, well, the squared norm, that is to take each element, we take its absolute value square, we sum it up, and that is the square norm of vector. Then we divide with this. Then we can see that this is matching very well with this formula here. 1 over m, summation of all the terms. Here it says xm, here it says xm absolute value square. So we sort of need to think about, okay, this looks like two notations, but they're different. So what is called xm here is the same thing as absolute value square of xm. Absolute value square is non-negative, so we satisfy that. The elements here are ID, so we satisfy that. So this thing here should converge to the mean value of each of these terms. And that is what I've written down here. You can take any index, any of these ones, because they have the same distribution, takes absolute value square, and this is going to converge to the mean value when you have a lot of elements in this vector. So what this means is the following. Say that we are computing the actual value of this one for one random sequence of numbers here. Then, depending on how many elements you have, you will get this red thing here that is jumping on. When it's small, there's large variations, but when you have like 10 or 15 or 20 elements, then it starts to approach this mean value, which is this value here, which is 1 in this case, but it's not so important. Then as you add more terms, there are some variations. They're moving away, then it comes close to it again, then it moves away. But as you can see here, as we are adding more and more terms with new independent randomness to this one, it starts to converge towards this mean value here. And when you have infinitely many terms, there will be a perfect match. And if you are looking at the interval where 80% of all our random variation is going to be, well, then it's between this upper and this lower curve here. And that's where we also are existing in this case. So when we are adding a lot of randomness together, they all are positive, then they are averaging out the variations. And that is what we're going to utilize now. So we will talk about the initial motivation of having many antennas that Thomas Merceta was putting forward in his first works. So what this idea was about was to say that, look, we have one base station. We have two users. They are sending signals, S1 from user 1, S2 from user 2. They are propagating over different channels to these antennas here. This base station have M antennas. What are we going to do with those M antennas? Well, we are going to use them in order to separate the different user signals. So we can assume that these vectors have the same length as the number of antennas. Say that the number of antennas is M, then HK from user K to the base station contains M elements. HK1 to HKM is a vector. And we can assign some randomness to it. Say that it's complex Gaussian distributed. So the real and imaginary part is Gaussian. And they have zero mean and they have an identity as their variance. Just some kind of randomness where all of the elements are independent, as I was mentioning before. Then both the users send their signals over their different vectors, channels. What we receive is the following. Receive signal Y, vector of length M, or so the signal received at each of the different M antennas. We add up what the first user is sending, what the second user is sending, and a noise vector, which is, we assume it's also independent, complex Gaussian distributed, zero mean, and variance 1 on each of the elements. Then, based on this received signal, the base station would like to extract the signal from user 1 and the signal from user 2. And these are sort of symmetric problems. So let's just focus on one of them, user 1. What we do is that we select a linear detector, a vector. I call it V1, V as in vector. And why do I select a vector? Well, because what we received is a vector, but what I'm interested in is S1. So somehow I need to take my vector, put it together into a scalar again. And that is what this linear detector is going to do. So what I do, I take my vector Y, I compute the inner product with this vector that I've been selecting. So inner product between received signal and the vector I'm selecting. This H here is a conjugate transpose. So it's a transposition where we are changing a column vector to a row vector, and it's a conjugation of the complex parts. And when we are computing something like this, we will get a scalar. And there are then 3 different parts. If we are taking the inner product like this, we are multiplying with V1 Hermitian from the left. We get multiplied with this term, with this term, with this term. And we will look very soon at these 3 different parts. But first, we will make an assumption of what V1 is going to be. My assumption is that it's equal to the channel from the use of interest, H1. And then I'm going to put a 1 over m in front of it in order to make use of this law of large number results. Okay, so let's focus on the first part. Here we have the desired signal, S1, and we have a term in front of it, V1, H1. And V1 was this channel vector, H1, and then a 1 over m. I write the 1 over m here. Then I have H1 as an inner product with, H1 again. So this is the definition of a squared norm of this channel vector. And then now we make use of that law of large number that I was saying. If we have a square norm of a vector with independent elements, and then we divide with number of elements, then if we have a lot of antennas, this is going to converge to the mean value of just one of these elements here, the absolute value square of, say, the first element. And from this definition here is equal to 1. So the term in front of S1 converges to 1 when we have a lot of antennas. Okay, let's look at the next term. This is some kind of interference. We have the signal from the other user, S2. We have an inner product between the V1, the linear detector of user 1, and H2, that is the vector from the channel from user 2. If we are putting in that V1 is H1 divided by M, we are getting an inner product between the user 2's channel and user 1's channel, and here we have 1 over M. And this is also summation over random things. And when you have many elements, it's going to converge to the mean value of each of these elements. Say the mean value of the first element. We take the first signal from the first vector and the first signal from the second vector, first elements. So that is what I've written down here. You should take the expected value of that. And my channels for the 2 users, they are assumed to be independent. So if you take the expected value of a product, it's the same thing as taking the expected value of the first one times the expected value of the second one. Both of them have 0 mean, so this is going to be equal to 0. So the term in front of the interference signal S2 is conversion to 0 when you have a lot of antennas. And when it comes to the noise term, you can make the same arguments again. We have an inner product between V1 and N. N is a noise vector. It has actually the same distribution and independence as the channel of user 2. So for the same reason, it converges to 0. So these 2 terms goes away asymptotically when you have a large number of antennas. And that means that the received signal, after I have applied my linear detector, when you have a lot of antennas, it converges to only the signal, no noise. And if you have a noise-free transmission, you can transmit as much data as you like. You can squeeze in, say, you have 1 million different options for the signal. And if you receive it without any interference or noise or anything, you can tell apart what 1 million options there are. And then you can send one huge amount of data at the same time. So that is sort of the initial motivation of Massive MIMO. When you have a lot of antennas, then we get a noise interference-free communication. But then we have the contamination, the nut. What is the problem here? Well, that is that in order to do what I just described, we need to know the communication channel. I was using H1, the channel from user 1. How do we learn it? Well, I was saying before that we need to send some kind of known signal in order to learn it. And the length of the signals that we can utilize, we had this tau c, that was the number of symbols that we can transmit before the channel changes. So it only makes sense to try to learn the channel within that frame. And out of that frame, I was allocating tau p as the number of transmission times, number of symbols that I can assign to learning the channels. So those signals that I transmit have a maximum length of tau p, which essentially means that there are tau p different orthogonal ways we can transmit. For example, first one user transmit, then another one, then another one, then another one, and so on. And then up to tau p users can transmit. And If you have a large network, that won't be enough. Maybe tau p is 20, but then you are in Istanbul or Ankara or some city with millions of people. It won't be enough. So some users will have to send the same pilot. And let's look at what happened then. So during the pilot transmission, we are sending some kind of known signal. Say we have a scalar here, psi. Both of the users are transmitting that signal. And then it gets multiplied with their signals, the channels, H1, H2. We have the same assumption as before. Then the received signal that I get during my pilot transmission is going to be H1 times the signal, H2 times the signal, or the pilot, plus noise, W. And if I'm interested in one of the signals, one of the channels, H1, then my estimate of this could be that I take Y, I divide by this pilot symbol. So I take Y divided by that, then I get H1 plus H2 plus a scaled down version of the noise. This is the best way I can extract H1, but it contains H2 and the noise here. And that is what makes it complicated for us. So if we are trying to do the same trick as before, when I'm receiving a signal, then remember when after I have transmitted data, I had this inner product between my own channel to use one and the linear filter. I didn't give it a name before, I would call it now maximum ratio filter, MR. And as before, I take one of them and the channel to the user one, except that now it's the hat here. It's the estimate of this channel. We put it in here. And now the problem is that H1 hat is containing these three different parts. And that means that if I compute this inner product, I should take the inner product with H1 and itself, that's the squared norm, H1 and H2, it's this term, and H1 and this noise vector here. Put it here, and then we divide with this pilot here. And if we now use the same argument as before, when we had a norm of a channel, well, then it converges to 1. And when we have two different random vectors, it converges to 0. So these two terms are going to go away, and this whole thing is going to go to 1. Fine, no problem, same thing as before. But when it comes to interference, the problem arises. So before this interference term, I had my channel to user 2, and I had my combining vector. When I now compute this inner product, I see, okay, I get an inner product between H1 and H2, it's here. Then I get between H2 and H2, oh, that is the squared norm. And then I get between H2 and the noise, no problem. These two terms are independent of each other, and these two terms are independent of each other, so they will cancel out. But this thing here will converge to the one coming from the channel. So the noise will actually go away, it will continue, because this noise here and the noise during the data transmission is different, but the signal and the interference remains. So as you increase the number of antennas, it turns out that we are getting the sum of the two signals and we cannot distinguish between them. And that is the extra thing that comes from pilot contamination. Why do we call it like that? Well, we are transmitting a pilot. It was meant for learning the channel to user 1. But user 2 is contaminating, is destroying that transmission. And in particular, it sort of injects its own channel here into the estimate. And then when I try to get rid of interference, that injection of this channel is causing interference to remain. So even if I increase the number of antennas, I can't get rid of it. So when I try to listen to user 1, I am accidentally listening to a bit of user 2 as well, and I can't get rid of that effect. So that is the pilot contamination issue. And pilot contamination is nothing new by itself. This is something that has existed for a long time. What can we do about it? Well, say that we have two cells, and we are serving the users in the blue cell, but we get interference from the second cell here. In each cell, there are 8 users. Within my blue cell, I have a signal noise ratio of 10 decibels. And then we have a very strong interference from the other cell. They are 3 decibels weaker, but still strong. Then if you are using formulas from like standard massive MIMO literature, the signal to interference and noise ratio for use in the blue cell will contain this expression here. So you get log 2 of this, or 1 plus this expression. It contains the signal part with M, the number of antennas. Here we have this SNRs. This is the estimation quality. This ratio is saying there. Here we have interference. We have K users in each cell that are interfering. I have the SNR for those in my own cell and those in the other cell. And then I have a noise here. And then I have an extra term that is coming from that pilot contamination that I was mentioning, that also grows with the number of antennas. So the signal part and interference term will increase as I'm adding more antennas, but the interference and noise will not, and therefore they will disappear. So if I simulate this and I add more antennas, let's say I start with 10 antennas, then I can see that if I measure the size of this term and this term and this term, the black curve is a signal term. As I add more antennas, it grows. I have logarithmic scale here, so linear growth here becomes this bended curve. The interference term is this one. It's independent number of antennas, so it just stays constant. And the pilot contamination is this term. It also grows linearly with the number of antennas, so it goes up like this. And in the past, all of the communication systems that we have been considering is down here, where we have a lot of antennas. Where we don't have so many antennas. And in that case, you see this pilot contaminated interference is very weak as compared to this desired signal, and also compared to interference. So if we add up the black and the red term, these two terms, the red term will be negligible. We don't need to care about it. And then if we are up here, when we have a lot of antennas, then we will instead have a situation where the red curve have now grown up to the case where it's above the blue curve. And now it's actually the pilot contamination that becomes a dominating factor as compared to the conventional type of interference. So that means that conventionally, we don't need to care about pilot contamination. It has been there all along, but now when we have a large number of antennas, we need to care about it. And then we, so it's sort of now a phenomenon to think about. So how do we actually deal with this pilot contamination problem? Well, some thoughts. A lot of people spend time on dealing with this before the time when we were trying to, when we discovered the solution that I will tell you about in a moment. So let me first give you a brief overview of those type of solutions. So the first one was to sort of knowing that, okay, a frame contains tau c signals. We can transmit tau c times within a frame, one so-called coherence block of frame. And people try to find ways of increasing the number of pilots from this tau p, which is a small fraction, up to the entire frame. That is sort of the most number of times we can transmit. We cannot make it better than that. And one way of doing it is to add a so-called pilot reuse factor. So if before we're describing a scenario in my simulation where I had 8 users in every cell, and user 1 in each cell is using the same pilot, user 2 is using the same, user 3 is using the same, and so on. Then now that is not the case anymore. Then what we can now consider is ways of trying to increase it. So not every cell uses the same pilot. Well, in a situation like that, we could say that every third cell or every fourth cell using the same pilots, and that means that for each cell, the neighboring cells are using different pilots. And we can assign it smartly in that type of ways. The drawback with such a solution, which is proposed in a number of papers, and the numbers here are referring to things in my book, Massive MIMO Networks, different references there. The problem is that if you now before had 8 pilots and then you're going to reuse them in every 4th cell, then you need 8 times 4, so that's 32 pilots, and that eats up quicker and quicker a larger and larger fraction of your frame, and the rest of it that you have for data will shrink. So that's sort of a problem. This method can also only alleviate the pilot contamination entirely if the frame is infinitely large, so you never really get rid of the entire problem. The second option is so-called data-aided channel estimation, where in addition to sending first some known things that are pilots, then we have data afterwards that are unknown. We try to sort of make use of both the pilots and the data and jointly use it to estimate the channels. The problem with that is inherently that the data is unknown, so it's sort of some kind of interplay. I estimate the channel based on the pilot, then I guess the data, then I try to improve my estimate based on that guess, then I try to improve my data estimate and iterate like that. It becomes hard, but under certain condition it works. So you can at least improve things if you do it well. The third option is something called superimposed pilots. Instead of first sending pilots and then data, we can send pilots and data all the time. Just as I was saying, when you send multiple use at the same time, they are sending data simultaneously. What if we are sending data and the pilot at the same time? We're adding them up. And then when we are estimating things, we are multiplying with the pilot, and we try to separate the pilot and data transmission. It's all complicated, and the main thing is that it actually is creating interference between the data transmission and the pilot transmission. And at the end of the day, we won't get any extra dimensions by doing something that we just create a lot of interference from it. So none of these ways were really the optimal ways of dealing with interference. So with this in mind, in Thomas Merceta's first paper on massive MIMO, he was writing that pilot contamination imposed fundamental limitations. And then he was updating that, or writing it more properly in his book, Fundamentals of Massive MIMO, where we say that all known capacity lower bounds approach a finite limit when the number of antennas grows large. And what this means is that if we have a spectral efficiency here, and you increase the number of antennas, then if there is no limit, it will just continue going up like this. And note that this is logarithmic scale. So then the signal to noise ratio will grow linearly, and you get a linear growth here. While if you have a finite upper limit, as he was claiming here, it will sort of go up and then it will converge. And if we can somehow improve our transmissions, well, the only thing we can do is that we can push the curves upwards, but sooner or later they will converge. And that also means that if we're using this maximum ratio method I was describing, where we're just taking the channel of a user and we are multiplied with it, and then we see what we get, that is not the best way of operating. We get a green curve. If we design something better, we try to cancel interference, do something called zero forcing, well then if you have a small number of antennas that could help, but eventually couldn't help. That was sort of the conclusion. But is this all that we can do? Do we need to accept that we always are going to converge to a finite limit? Or can we reach the nut inside of this one? Yes, we can. And what we need to remember is that so far, what I have assumed is that these channels to the users are so-called IID Rayleigh fading. The elements are independent and identically distributed. And practical channels aren't like that. Here is from Lund University, a measurement they did on a long array. They put up antennas on an 8-meter long array, and they measured the channels to different locations. And what they saw is that they had 128 different locations, and here is the powers. They have power variations along it to the user. So different antennas hear the signals from the users differently strong. So there's like 3, 4, 5 decibel variations here. So if we take the channel vector, we take an outer product, we compute the expected value. This is a so-called correlation matrix. Then along the diagonal, we have these elements. And these elements are going to have variations, power variations, and that is leading to some kind of variations along the diagonal matrix like this. In addition to that, each user have some other unique things. So if you are looking at the different antennas, and then we look in different angle or direction to this antenna, from this angle, this angle, this angle, how much energy comes in here? Well, when there is a red color here, there's a lot of energy. When there is blue color, there's little energy. And we see that those things are also varying between different antennas. So some antennas get a lot from some angles and some from other angles. There's some pattern here, but there is some kind of unique signature here of strongness and weakness in different angular directions, which is sort of turning into different variations in the off-diagonal elements that is saying how these different elements are being correlated with each other. So everyone have a unique so-called spatial correlation matrix. And I wasn't the first that was pointing this out. There were several nice papers that were saying that suppose it's like this. Every user, user 1, 2, 3, and 4, they are having signal that comes in from distinct angular directions. Some from direction 30, some from, yeah, what is this, 70, 80. Here we have 120, and here we have 170. And there is a band of some angular interval there, but there's nothing more than that. This is called a one-ring model, where the signals are coming in from distinct intervals. If it's like this, then when I would like to tell these users apart, I just need to say, I'm going to look in the red interval, or in the green one, or in the yellow one, or the blue one. And when I'm looking in one, I don't see the other signals. In that way, I can learn the channels at the same time. This user can send the same pilots, because I know that the signal from user 1 comes from this in this interval, the signal from user 2 in this interval, and so on. And if you create these covariance matrices or correlation matrix I was mentioning, you can take the inner products to become 0. And this is a very strong assumption, because in reality, it doesn't look like that. When they measure this at Lund University, we definitely see that it's sort of like the yellow users have some intervals, the red ones have some, the blue and the green one, they are confined in small intervals. The red one is more like someone had thrown paint on it. And this is when we actually are seeing the base station from the user side. When we are not doing that, well, then it's more like a child who has been painting back and forth here. All of the colors are at one. That said, it's not a coherent structure here. It's not like all the colors are always on the same place. Everyone has a unique type of pattern here, but so they are different, but they are not separable like this. They are mixed up. But we can still use this to crack the pilot contamination. So let's start over with the same model as before, but with spatial correlation. So each of these channel vectors has a Gaussian distribution. They have 0 mean, but they have a correlation matrix. This matrix is describing the spatial correlation. The users are sending the same pilot, psi, and the received signal is just as before, equal to this y here. And now you can open your textbook on estimation theory and say that if I receive y, how should I estimate h1 from it? Well, before it was just dividing by this received vector, but now we can do better because we know what these matrix are going to be. So the optimal estimate is called the MMSC, minimal mean squared error estimate. And in order to do that, we take the vector y, we multiply with the inverse of the correlation matrix of the received signal here. So y Hermitian expected value. It's correlation matrix user 1's channel, user 2's channel. We have the identity matrix coming from the noise, and then we have 1 divided by the pilot here squared. We put it here, then we put the correlation matrix of user 1 here, and we have 1 over the pilot, and that's it. And since y is Gaussian distributed, when we add up 3 Gaussian things, the estimate is going to be Gaussian distributed, and one can show that its correlation matrix is the original one minus something that has this shape. The estimates are the 2 users. I can apply this for user 1 and 2 by just putting 1 here or 2 here. If you compute it, they're in the product. We have H1 here, we have H2 here, put it here. Then what is going to be different? I'm going to have R1 from this one. And then I'm going to get Q inverse. Then we'll have Y. And then I have the conjugate here. I get Y 1 more time. I get the Q 1 more time. And then I get Q -1, I get R2 here, and maybe this term here is missing. It should be one more term like that, but it gets this type of shape. And that means that these channels are correlated with each other. But if we are taking these two descriptions, H1 hat and H2 hat, this part is the same, but this part is different. So we can turn H2 into H1 by first removing this part. We take for H2 hat, it says R2 here. We take R2 inverse, then we multiply with R1, and then we have the expression for the estimate of user 1. So H1 and H2 are related to each other. They are linearly related like this, but and they're correlated, but they are not the same. They are vectors pointing in different directions. So say H1 hat points in one direction, H2 hat points in another direction. This is something that can be utilized because now there is directions that are in the orthogonal to one of them and not the other one. This is going to be the key for us. So the method to solve the pile contamination problem is to utilize that. What we once again want to do is to select the receiver, V1 for user 1. We multiply it with the received signal Y, still containing the signal transmitted from user 1 at the data transmission from user 2 and the noise. And if we are separating this up into 3 different terms, we have the desired signal, we have the interference, and we have the noise. Same kind of things as before. Then one can compute an exact expression for the actual performance, actual spectral efficiency. One can talk about channel capacity and things like that. And since we have a random channel, there are going to be some expectation with respect to randomness. So the spectral efficiency of user 1 is an expected value of log2 of 1 plus an SINR expression that looks like this. What it contains in the numerator is this term here, V1 Hermitian H1, but not H1, the true one, but the estimate. The interference term is going to contain this term here, V1 Hermitian H2, but not H2 itself, the estimate. And here we have the noise, V1 Hermitian. We have the noise, we average over the noise, we get covariance matrix sets. We have V1 and set contains the noise term, and it contains these estimation errors. Okay. And what we can do when looking at this signal, interference, and noise is that we can choose V1 to be orthogonal to the estimate of user 2. That was what I was describing. We can pick V1, so it's orthogonal to H2 hat. That means that this term can be made 0. We can take this interference away. And at the same time, making sure that the numerator is not going to be 0. So we can take out the interference without taking out the signal. And now there shouldn't be an interference left. Well, it could be a problem still that even if this one is not identical to 0, it sort of disappears asymptotically when you have a lot of antennas. And that is something, no, it doesn't have to disappear. It could be that even if we take out this term here, if this term is not increasing with number of antennas anymore, we still won't get something that is increasing. Then we will still be left in the case where we have a gamma that is going to approach the finite number as we have more antennas. So here we have the trick, selecting the combining vector to take out the interference. And what remains to be shown is that the remaining term is going towards infinity. In order to do that, we need certain machinery. We need to say that, okay, the SINR have a certain shape. We can write it as V1 here in the matrix containing H2 hat, H2 Hermitian. We have the set here. This is a so-called generalized Rayleigh quotient, and those ones are known how to optimize. There's an optimal shape called the MMC receiver. I'm not going to go into every single detail in this part here, but there's a way of finding the optimal way of maximizing these ones for given estimates. And in order to show what happens when you add a lot of antennas into a system, we need to make 2 assumptions. The first one is that if we take a spatial correlation matrix of a user, we take the trace of it that is adding up the power along diagonals. and we divide with the number of elements, then when we add more and more antennas, this is going to stay greater than 0. That essentially means as we add more antennas to our array, we are capturing more and more energy, which is sort of logical, but we still need that technical assumption. The second thing is that if you take the covariance correlation matrix R, we are computing the 2 norm. That is the largest singular value, or large. You can view it as the largest eigenvalue of this matrix. Then it should be smaller than infinity, which sort of is saying that as we add more antennas, the energy is going to be spread over many spatial directions, coming in from different directions, not just from one, which is also something that's happening physically. Next, we have our 2 users, user 1 and user 2. I assume now, if you remember those colored plots there, where one user had one pattern, another user had a second pattern. Now we'll get a mathematical meaning that those patterns are different. Namely that the 2 covariance matrices, R1 and R2, are linearly independent. What that means is that if you add them together, we multiply them with some scalars, lambda1 and lambda2. We add them up, we compute the squared norm of it, we divide with number of elements, then this is, if we take the smallest number that we can get here, when one of these 2 is 1 and the other one is 0, it remains greater than 0. Sounds very complicated. What it essentially means is that if they are linearly independent, we can't take one of them and subtract it from the other one and get 0. So that is sort of the idea. Here is an example that's telling this a bit much more. Say that we have one correlation matrix, which is an identity matrix, one which contains 2 identities, but one of them is twice as strong as the other. So it's not an identity matrix in total. Then if you compute this expression, I need to put one of lambda1 and lambda2 to 1. Say we put the first one to 1. Then we take the squared norm of this thing. We put in the expressions. We get this term here. Here we have n terms, which contains 2 plus lambda2 times 1 from this one. And here we have n minus 1 terms. We have a 1 from here. We have a lambda square from here. We have this term. Then the next thing it says is that we should minimize this expression with respect to lambda2. You can take the first derivative of this one, put it to 0, find the minimum term. We get this expression here. And from this, you can show that as the number of antennas goes to infinity, if n is constant, we can see we have m here, we have m squared here, then it's going to go to 0. So in that case, it's they are not linearly, asymptotically linearly independent. But if we say that the part here that is contained in 2, this one is not having a given number, it's a fraction of n. So as we're increasing m, we're increasing both of these parts. And alpha is telling us what fraction it is. In that case, you put this expression in here, and you will see that this simplifies into 1 minus a, or alpha, times alpha, which is greater than 0, if alpha is between 0 and 1. So in that case, we have asymptotic linearly independence. These matrices are always linearly independent. We cannot never subtract R2 from R1 and get exactly 0. But it sort of say that the subspace here, n-dimensional subspace where they are different, cannot just be small. It needs to increase with the number of antennas as well. Then we have this asymptotically independence. And then we have sort of these color patterns that are sufficiently different. They're not just different in a finite number of pixels, but if we make it larger with more antennas, the number of pixels that are different becomes larger and larger. Then under these 2 conditions, assumption 1, assumption 2. Assumption 1 was this about that the trace and the norm of the correlation matrices have certain properties. And number 2 was that the 2 users that are using the same pilots have different correlation matrices that are asymptotically independent. Then the SINR grows unboundedly with the number of antennas. This is something that we proved in the paper called Massive MIMO has unlimited capacity. I'm not going to go into the proof more on this. I'm just going to briefly say that you can extend this to cases with not only 2 users, but many cells, many users. The important thing is that you have a finite number of users and cells, and then they can reuse the pilots in any way you like. All of them can use the same ones, or they're reused in any way you like. Then you let number of antennas go to infinity. As long as the pilot sharing users have correlation matrices that are linearly independent, you get this result. All of the users have an SNR that continues upwards. They're interfering with each other, but they're not limiting each other. You can do this in a downlink. I exemplified in the uplink. You don't even need to know these correlation matrices entirely. Just remember what I was saying, that you have different power variations along the diagonals of them. As long as that is the case, we don't need to know what's on the other parts of matrices, which makes it much easier to learn this in reality. So just to start to wrap up now, what we need in order for this to work is that you have rarely fading channels as before, but we have a little bit, just a small, tiny bit of different statistics for different users. Here is a crazy setup that I created. We have 4 base stations. In every cell, we have 2 users, the star and the plus sign. And the plus signs are using the same pilots in every cell, and the stars are using the same ones. And I'm putting them all in this shaded region, which is sort of the worst part of the cell. And for my user in my own cell, I have a bad SNR and have an even slightly worse SNR to the users in the other cell. Then this is what happens for the spectral efficiency as I'm increasing the number of antennas. For every user, when I have small number of antennas up to 100 antennas, then the different curves is for different methods. Match filter, that was this maximum ratio type of thing that I was doing in all of my mathematical examples, and where we saw that it converges to a limit. That one is the blue curve, and you see that it converges as we have more antennas. If we have something slightly better, like zero forcing or regular zero forcing, that was I was showing before as well, that if you use something better, then it makes it different when we have a small number of antennas, but then it converges eventually. But if you use this optimal receiver that I was describing, that is going to use this different correlation matrices to cancel interference between the users. When you have sufficient number of antennas, the curves are decoupling, and this one is just continuing upwards. So what does it tell us? We can always handle more traffic, more data requests from our users by adding more antennas. Then, of course, going upwards here, we have logarithmic scale. So it's sort of, there is diminishing returns by adding more antennas, but we can always benefit from it. And that is why I say that you have an unlimited capacity, because if you have a certain capacity, certain spectral efficiency, and you need more, you can always add additional antennas and achieve that. And I think of interest of time, I'm not going to go through there was some related work that was touching upon this, something called the pilot contamination precoding for multi-cell setups, and some other things called bilinear equalizers that was also touching upon the same result before we discovered it. So to wrap up, what are the lessons learned? Well, I think that what I realized after discovering this thing, after taking my pilot contamination and actually cracking it, was that these schemes that we saw that was conversion to a limit, these were designed for one cell. People designed it having one cell with one user or multiple users, and maximum ratio was for one user, zero forcing was for multiple users, but within each cell. And then we just applied it in this large network without redriving anything. And it didn't work. And we thought that this is the best thing we can do. But we actually need to always go back. If we extend the range of our problems, we cannot take a good solution to a sub-problem and apply it to a bigger problem and believe that it's still going to work. We needed to actually utilize a lot of different things in order to deal with interference, deal with this extra pilot contamination that's always coming from other cells. And we should be careful from extrapolating results. To be fair, everything Marcetta was doing in his work was with independent and identical distributed fading. And then maybe him, or at least others, were sort of having the impression that those results were holding in general. But it turns out that it was only on those assumptions where pilot contamination gave rise to these things here that converges in all other cases, it goes up like this. So if we are sort of comparing cases where we have, we are varying the correlation. If we have no correlation, 0, then this optimal method that is using the spatial structure, and the other methods, there's no difference. But as soon as we add a little bit of correlation into it here, going up along this axis here, the curves decouple. And another thing that I think is sort of a lesson learned here is that why did everyone consider ID rarely fading? Well, if you look at the book by Thomas Morissette, it's very thin. That's because with that assumption, you get very nice math, analytical tractability. And in some cases, this is very good. You get nice expressions, you can understand those expressions. But the problem is also that they can be misleading. There is a risk that the expression that you are getting is telling you something that isn't right. And in this case, it told us that pilot contamination was a nut that we could not crack. Finally, there is the Arthur C. Clarke's 3 laws. Arthur Clarke is the author who wrote the 2001 Space Odyssey, for example. And he was thinking a lot about the future developments. And he wrote 3 laws. The first one was that when a distinguished but elderly scientist states that something is possible, he's almost certainly right. And in this case, I would say that massive MIMO is possible. That was what Thomas Morissette was claiming, and he was right. Now it's here. When he states that something is impossible, he's probably wrong. And when it comes to that pilot contamination will be a nut that we cannot crack, that's wrong. Law 2, the only way of describing the limits of the possible is to venture a little way past them into the impossible. And in this case, what we needed was a tool, spatial correlation, and in order to actually redesign our receivers optimally for having the spatial correlation and the multi-cell structure. In that way, we can crack our nut. And 3, any sufficiently advanced technology is indistinguishable from magic. And I would then say that massive MIMO sounded like science fiction 10 years ago, and now it's a mainstream technology where Huawei have sold 1 million of these space stations. With this in mind, I have defined what I call massive MIMO 2.0. This is a system that have many antennas, many users, that is operating in a way I described, and that is exploiting this spatial structure of the channels from the beginning in order to make the system work better. And you can read more about this in a paper called Towards Massive MIMO 2.0, where we really are saying that the next problem to solve is actually to learn the spatial structures, the spatial correlation matrices, R1, R2, and those things. With that, I would like to thank you for listening to me for a very long time now. And you can listen even more to me on my YouTube channel, listen to me talk about massive MIMO and other thing in my podcast, Wireless Future. And if you want to read more, you can download my book for free from massivemimobook.com.
Okay, we thank again our guest. Thank you very much, Dr. Björnson. We will be starting the Q&A session. So I need to make very quick announcements. So you can either ask your question by raising your hand so that we can let you to activate your microphone. That will be the best option. You can write to chat, or if you are watching on YouTube, if you comment, add a comment, then we will be directing your questions to our guest today. Thank you again. Barış Hocam, do you want to say anything?
Thank you, Professor Björnson. It was a really lovely talk, and I am very happy to see you and hear you. I have a few questions, if you don't mind.
Sure, I'm here.
Okay. I'd like to ask you about the side lobes, the effect of the side lobes when using massive MIMO. You said that the law of large numbers tells us that the interference goes away in the first example that you have given. But what about the side lobes?
Yeah, so what this is sort of building on, that every time we add a new antenna, we are sort of making the arrays wider. And the the main beam, when you're beamforming in line of sight, is inversely proportional in angle to the number of antennas. If you make it wider, then if you make it 10 times wider, the main beam will go down by 10 times in angle. And since that also concentrates the energy in that main beam, then there will be more and more side lobes, but they will be weaker and weaker. So it's the same energy, but you focus it more, and you have ripples, but they contain less and less.
Yeah. Okay. And another question that comes to my mind is, what's the performance of this pilot contamination interference when we perform blind channel estimation or pilot blind channel estimation?
Yes. So then it sort of is open up a new problem. I mean, to have pilot contamination by itself, it sort of assumes that you send a pilot. So if you are doing something that's entirely blind without any pilots, there is no pilot contamination in that particular way. But then there are other challenges. How can you identify users if things are entirely blind? And there are some nice works by David Chespier, David Gaspert from Eurocom, and Miller and others that are working on those type of things that I can recommend in general. But I think usually they are starting with having some pilots, and then they use the data in addition to it, so that you have some ability to separate the users and then improve with the data.
Okay, thank you. And one more thing, when we read the specifications for 5G from the ETSI documents, we see that there are two types of beamforming, the type 1 and type 2. And I think that they are static types of codebook typed beamforming methods. Can we still apply what you tell in these types of codebook beamforms?
So I don't know every detail on the standards, but as far as I understood, there's sort of two modes that use codebooks, and then there is a third mode that do more what I was describing. So what this sort of is meaning is that the problem, if you are using codebooks, is that now the base station is transmitting, it's guessing on a number of different directions. The users are feeding back signals to say which direction worked well, and that creates other types of issues. And if you have very many antennas, you need to sort of search many directions. So that is not recommended. But it's sort of the simple way of implementing. So I think all of the commercial base stations today are using it. But then there is the other option to let the user send an uplink signal and estimate, which is also there. I think it's called an SRS.
SRS based, yes.
Yeah, and I think those options exist. I was writing in my blog recently about measurements where they did that with 16 data streams. It's possible to do within the standard. And I think that is the future as well, but it's probably harder to implement because that's not what people have been used to implementing.
Yeah. Thank you very much.
Thank you.
We have some questions from our visitors. Mohammed Bey, I will ask you to unmute. You should be able to unmute yourself. Mohammed Bakürek. If you're not available, Feza Hocam, would you like to ask now? You can unmute yourself.
Hi, thank you very much, Emil. It was a pleasure to listen to you. It was a very intensive talk. My question is about the resilience of the massive MIMO networks with respect to dense multipath environment. In the urban environment, we have very significant amount of multipath, and with respect to the indoor channels, it's another story because there are walls and objects and people are walking around. So how effective is this standard Rayleigh channel assumption in such an environment?
So I think, first of all, I was also making the assumption of Rayleigh fading to simplify the analysis. I think having some other type of channel distribution, but still having spatial correlation different for users will be enough for these results to appear. I think there are two aspects to it. I think when it comes to the variability of the channels, the problem is sort of the same as we have had in other systems. We need to estimate the channels as often as before. When things are moving a wavelength, we need to re-estimate it, and the multipaths will be the same kind of situations. Then let me see what's the other thing I had in mind.
When you have a dense multipath environment.
Yes, and so it's sort of that is sort of determining what your delay spread is going to be, and then this coherence bandwidth is inversely proportional to delay spread. It's sort of a simplification of the things, but I think these models by themselves are applicable in any situation. It's just that you need to select your frame size to match with the time and frequency variability of your channel. I think what might be the bigger problem is really that it's based on that there is this spatial correlation matrices and we can learn them. And how do we create random channels in the system? Well, it's sort of based on that the user is moving around in a small area and creates new random realization according to a distribution. And as long as that is happening, things are fine. But if the person is moving around in the world and move down the street, then is there statistics? Is there a correlation matrix of its kind? Well, maybe piecewise in certain region is going to be there. Can we learn it? Well, yeah, I don't know. That is where the difficulty is in extending the models to reality appears.
Okay, thank you.
Thank you, Feza Hocam, for the question. Izzet Sağlam Bey, would you like to ask your question in person, or should I read your question from chat? You can activate your microphone if you want.
I've been to Linköping in 1997.
Wow.
With respect to the COST project, COST 251, I have visited the Defense Research Agency there. It was about HF communication, actually. And I gave a talk on the scatter plots for multipath on HF channels. So it was an interesting coincidence that you are from Linköping and you are talking about the massive MIMO channels. That's why I remembered the multipath problem.
Yeah, we have some collaboration with still that defense agency that is there.
Izzet Bey, are you available now to ask your question? Or should I?
Yeah, thanks for the great presentation. I have actually two questions to Mr. Emil. My first question is, does MAC layer scheduler have effects on massive MIMO and pilot contamination? And my second question is there any relation between the massive MIMO 2.0 and the coordinated multipoint COMP? Thank you.
So the first question there about this scheduler, I think here, in an effort for me to sort of say that, oh, we have the pilot contamination and now we're going to get rid of it, in a way, in order to show those plots where you saw the curves were separating, I've sort of purposely created the worst kind of scheduler, where users that are close together are using the same pilot, and then that this phenomenon appears, and then we can get rid of it. Just so I can simulate up to 1,000 antennas and see the effect. If I have a better scheduler where I'm sort of assigning pilots to users, first I avoid users that are very close to each other if I can, to schedule them at the same time. And if I need to do it, I am giving different pilots. So you have a large SNR difference between users that use the same pilot. Then you will push this separation of the curves upwards. And I would have had to simulate 10,000 antennas before I would see the separation. So then you can say that, oh, if you use this kind of methods, a good scheduler, then this won't be a problem in reality. but it also depends on sort of when I talk about many antennas, I also talk about a long array. If you have a panel, you will need even more antennas to separate things well. So yes, a good scheduler will always be useful, and particularly when it comes to assigning the pilots in a smart way. When it comes to COMP and Massive MIMO 2.0, no, I would say these are two different things. What Massive MIMO 2.0 is about is to empower each base station even more to deal with interference that it sees and utilize structure, utilize spatial structure of different users' channels in order to do that on its own. COMP or coordinated multipoint is instead of about having multiple antenna, multiple base stations that are cooperating in order to cancel interference, which is either an alternative or the next step. Sort of first you empower its base station to deal with all the interference locally. When there's something left, you could let the base station cooperate to take care of that. Or you don't improve the base stations, but you cooperate instead in order to deal with interference. So you can combine them.
Thank you very much for the question and for the response. Doğa Gürginoğlu, would you like to ask your question in person?
Thank you very much. I think my microphone is on now.
Yeah.
Thank you for this beautiful presentation. You have covered various recent topics and various important ones, especially in the Q&A session as well. I would like to ask about utilizing this spatial correlation information. Let's say in the beginning of transmission or reception, we have no information about the spatial correlation of the channel. How can we estimate the correlation matrix? As far as I remember, it was the only components were the diagonal ones. So will this be a receive signal power-based estimation of the correlation followed by normalization? And the second question would be, we had this spatial signature, but I think it was only on the azimuth direction. And as the non-terrestrial networks are also evolving, which is also an important topic for 6G. We will also have the third dimension, because like while on the ground, like we have pedestrians, drivers, and etc. The elevation angle is not usually that important, but when we have our UAVs, we have our connected planes and flying objects. We will also have a third dimension in the spatial signature part. I think that model can be extended, right?
Yes, so if I start with the second question, then yes, so what I was showing was these measurements from the Lund University where they had just a one-dimensional uniform linear array. And when you have that, you only have resolution in the angle domain. But if you instead have a panel, well then, as you're accurately saying, you can see things coming in from different elevation angles and from different azimuth angles. And that would give you yet another dimension to throw out colors from which directions are the different multipaths appearing. Then what else can we do? Well, I guess the next question was about the how we are learning these channels. And yes, if you only want to learn the diagonals of these correlation matrices, that was the question, how you estimate them. The diagonals you can estimate in this power manner that he was describing. So you're sort of say that you're observing the channel 50 times. And if you just compute the average power on each antenna on this 50 times, and you average on antenna by antenna, then you get an estimate of what you have on the diagonals. If you would like to instead estimate the entire thing, you will need many more observations. But essentially, it's still like taking sample covariance matrices. You get an estimate of the channel, you take the the outer product of it, and then you sum it up and average over many of them. And then there are some smart methods of how to do that I am describing in that Massive MIMO 2.0 paper as well.
Thanks again. There are two more questions here, and there are some questions on chat. I will read them after giving maybe asking Emad Farooq Ibrahim. Do you want to ask your question in person? You can.
Yeah. Hello everyone. Thank you very much for your presentation. I have only one question. Based on what I understand, that we can solve the problem of pilot contamination, given that we did MMC and using practical type of channel, correlated channel. But I guess that this assumes that we know the covariance matrix, not only between the base station and the user in this particular base station, but also between this base station and all users in the network. I'm not sure if this is right or wrong, but if it's right, so how we could know the covariance matrix between one base station and all user in the network?
So the receiver that I was describing is of that kind that you said that each base station needs to know the correlation matrix from itself to every user. And that would have a large complexity to learn it. Somehow the user using the same pilots will have to send some kind of signals, send pilots that you can utilize in order to estimate these type of things. So there are some problems involved with that. Then in the papers that I was just very briefly mentioning in my presentation, if I share my screen again here and jump backwards. Yes, so when it comes to this last case here, a bilinear equalizer for massive MIMO systems, here they are simplifying a lot what kind of information you need to know, and they show that even if you don't utilize the optimal receiver that I did, you can still achieve this effect of getting the capacity increase. And then it turns out that you don't need to know everything. Essentially, I think you need to know the covariance matrix to your own user, and then the sum of the covariance matrices to all of the other users, which I think is much easier to estimate. If you learn your own matrix, if you know that one, you can just take the received signal every time that someone sends a pilot. You compute a sample covariance matrix of that one, then you get a estimate of the covariance matrix sum of all the users that use that pilot. Then you subtract the one you know from your own user, and then you're there. So that's essentially how you can do it. But this is something that several of you were touching upon. This is sort of like saying that fundamentally there is no limitation. If you know the statistics, which we always usually are doing in information theory, then you can get the capacity towards infinity. But in practice, you're sort of switching the problem. Now it's no longer the pilot contamination per se that it's a problem, it's how you get outside the information that you need in order to deal with it. And that is then the next challenge, which is sort of the focus on that Massive MIMO 2.0 paper.
Thank you again. There's one more hand. Hashem Muradman, are you available to ask a question in person? You should be able to unmute yourself now.
Hello, thank you for your presentation. I have a question about one of your slides. I have seen, in fact, some papers that use DOA, directional arrival, for pilot allocation. But in one of your slides, there was a diagram that said it's not possible to distinguish between different users based on their directional arrival. So I want to know whether those papers are justified or not.
Yeah, this thing here. So, I mean, a paper like that, now I don't know exactly what assumption was made in that paper, but I think on the one hand, they are touching upon an existing property, which is sort of that users have signals coming in from certain directions, and some users only have signals coming in from a distinct set of angles. There's only one scattering cluster. Then I think the models that 3GPP are using is sort of, okay, there are 6 scattering clusters, and I think the general thing is that there is spatial correlation. It looks rather random if you look at the measurements here. There is a structure. The structure is random, like if you are making too strong assumptions on the structure, like having that it's just these nice bands here, there is the risk that you are developing results that are too optimistic. They will only work in very specific scenarios where you can observe this, like users standing on an open field in line of sight, the only signal comes directly from you and bouncing on the ground next to you. Then you can probably generate what you see on the left. But in more complicated scenarios, you can't. So if you develop such algorithms, they will work in certain scenarios, but you can't build a system that relies on something like that. And it might work better in millimeter wave systems than in lower bands, where you sort of are. If you have less reflections, all these figures I was showing will contain less color, and when the weakest colors are disappearing, they might have a more simple structure, and that might be possible to utilize. But I really prefer utilizing that there is a correlation matrix with some unknown structure, but it's there, as compared to saying there's a correlation matrix and it has this specific structure with its bands or anything like that, because I think then we are at risk of making such strong assumptions that we cannot have in reality.
Okay, there are a few questions on the chat box. I guess they can't unmute themselves. For example, Mr. Pakrek asks, could you give more details for pilot orthogonalization techniques you mentioned a little bit? Which technique or technology is most optimal to mitigate pilot contamination?
Yes, so I would say that if you have a certain number of pilot sequences, say 10 pilot sequences, then there are 10 orthogonal sequences. You can create something in between, but it won't really help you because they won't then be partially overlapping. So the question is really about, okay, if you have these 10 sequences and you have 100 users divided between different cells, how do we pick the users that are going to use the same ones? And that is a complicated problem. I mean, it becomes a combinatorial problem, and I would start by designing something that is sort of based on SNR differences, saying that those users that are at the edge of the cells that have low SNRs to the base station, they should pick pilots first, and they should pick such that they are not interfered by someone who is close by, and then you should build it up around something like that. But it's also easy to design the good algorithm. So I see in the chat here that reinforcement learning, for example, is mentioned. And yes, combinatorial problems like this, if pilot contamination is a problem for you, then I think machine learning tools could be utilized to sort of explore how to build a good algorithm, because combinatorial problems are always like hard to design low complexity algorithm for a person. But yeah, it's really about the SNR differences between users, and if you have a spatial correlation, you factor in how different the correlation matrices are as well. Users with very different ones could share pilots, and they won't interfere much with each other.
Another question. Mr. Etçibaşı is asking, are these results applicable to millimeter wave channels? I guess
yes. In general, they are. So in those cases, I would say that these correlation matrices will be or the coloring there will be much less, and then you have even stronger spatial correlation. So it will, if you can learn that information, it will be even easier to deal with the pilot contamination problem. Then I think another issue might, or usefulness might be that in the millimeter wave bands, you typically are physically protected against interference. So the signals are not leaving the room where you are very much, or if you're out in the street level and put up this kind of things, you can only get interference along the street and not around corners. So if you're limiting the area where the users could be, then having so many users there inside that area so you cannot give them orthogonal pilots might not be realistic either. So I would say that the real issue with pilot contamination is at lower frequencies where you have little bandwidth. So you will like to multiplex a lot of users. And in order to do that, you will run out of pilots. And that is when you need to deal with things like this. And the coverage is large, so the interference is leaking from many places.
And maybe the last question, what is your intuition to model this pilot contamination for reinforcement learning?
Yeah, I haven't looked into this myself. I think in general, there is this tendency of thinking that any problem that we have can be solved with machine learning. And when I am sort of interviewing new doctoral student candidates, just are sort of saying that everything that has been designed in the past is so bad, and now we're just going to put machine learning to it. So what you can read between the lines, and I think that there is a lot of good things that have been solved by man-made algorithms already, and we need to sort of identify those things that are not so easy to solve. But this might actually be something that is a good application for machine learning. Because it is inherently a combinatorial problem. It will be hard to develop good algorithms by hand. And if you're considering scenarios where the algorithms that exist, there is something called smart pilot assignment or some other algorithms that I've been mentioning in some papers. Then reinforcement learning can be utilized. And exactly what kind of cost function you should optimize there, I would there you need to make a sort of a decision. Is it that you would like to optimize the sum rate, or is it to optimize the worst users rate? I think I have some simulation in my Massive MIMO book where I'm also showing that as sort of saying that I have users, fixed channels, and then I randomize who is getting which are the pilots. And what I see is that the variations for different pilot assignments when it comes to sum rate might not be so large. What is the large difference is for a particular user. If you're at the edge of the cell, you can either get a good performance or bad performance, depending on what pilot you're getting. And that might not affect the cell-wide sum rate very much, but for that user, it will make a huge difference. And if what really matters is that everyone gets a sufficiently high data rate to stream their Netflix video, then it's sort of a metric like that, focusing on the weakest users that should be utilized in as a cost function in some kind of machine learning approach.
Thank you very much, Professor Björnson. I would like to remind everybody that Professor Björnson has a GitHub repository. There are a lot of documents and codes that I found useful. Maybe you guys will find it useful too. And also, I would definitely suggest the YouTube videos and the podcasts of Professor Björnson. I really find them very useful. And I would like to thank one more time to Professor Björnson on behalf of our department for accepting to attend our seminars. It was very nice to hear you, and it was a very powerful presentation, I guess. Thank you again.
Thank you very much for the invitation. And
No
thank you
problem.
for staying and listen to me. I said we're going to talk for 1 hour, then I talked for 1.5, I guess.
No problem, but it was very, very important subject. And other professors of this department would like to be at the end, but I guess they had some things to do. They told me that they would like to talk with you again. Maybe we can talk in another time for future possible collaborations. We would like to talk about this blind channel estimation topic of this pilot contamination not problem.
Yes. Thank you very much.
No problem.
Thank you again. Thanks to everyone who joined us today. We will be continuing our department seminars regularly. We will be announcing the next presentations in our website. Thank you, Professor Björnson. Thanks to all of our visitors again. This is the end of our event today. Hope to see you in our next events. Have a good weekend, everyone.
Bye.
Thank you. Bye-bye.
Bye. Thank you.